All right. So far, looking at the series that we've looked at so far have all been positive terms. Now we're going to look at series with alternating signs. The following test says that the terms of an alternating series decrease towards zero in absolute value, then the series converges. So my alternating series test, which we're going to abbreviate AST, if I have a series, of course, here's the negative 1 raised to n or n minus 1. That's going to be my alternating sign. And if my b sub n, okay, like it said, an absolute value, remove the negative 1 being multiplied to it, look at b sub n, and if b sub n always gives you positive terms and they're approaching 0, decreasing towards 0, then we can use this test. So if we can satisfy that the limit as n goes to infinity of b sub n is equal to 0, that's what should be happening if we're heading towards 0. So that's our first requirement. And our second requirement to show that b sub n plus 1 is less than b sub n for all n, which means my b sub n sequence is decreasing, then the series is convergent. So in this picture over here, here's kind of what's going, so you can get an idea of what's happening here. So we start at 0, you add on the b sub 1 term. That's your first partial sum. Then you subtract the second term, takes you backwards. There's the sum of the two partial terms. Then we add the third, subtract the fourth, add the fifth, subtract the sixth. So this is going to keep bouncing back and forth, back and forth, back and forth. So there's going to be my sum somewhere in between here. So it should converge. So does the alternating harmonic series converge or diverge? So number 1, take the 1 over n, that's your b sub n. Let's take its limit as n goes to 0. Yep, that's true. It's approaching 0. We're good. Number 2, now we got to show that b sub n plus 1. So you put n plus 1 in for n. That's 1 over n plus 1. Is that less than or equal to 1 over n? And if we cross multiply this, n multiplied up and over to the 1 on the left, the n plus 1 multiplied up and over to the right, gives us n is less than or equal to n plus 1, which again, you could subtract the n's and get 0 is less than or equal to 1. Or if you can see, hey, this is always going to be bigger because I'm adding 1 to the n. So that's true. So both of my conditions are true. Then we can state that this original series, this alternating series, is going to converge by the alternating series test. Example 2. Here we have a series. N equals 1 to infinity. We have negative 1 to the n minus 1 power. We have e to the 2 over n power. Do we converge or diverge? So again, remove the negative 1 to the power. This is my b sub n. Let's take its limit. So the limit here states, okay, 2 to the n power. Wait a minute. My exponent, top is the same, bottom's getting bigger. This exponent is approaching 0. So e to the 0 is 1. Wait a minute. That's not equal to 0. I violated my first rule. Okay, there's no reason to do the second part. And this is what's really convenient about this alternating series test here. So if this does not equal 0, then by the divergence test, this is not going to equal 0, the original sequence with the negative 1 on it. So by multiplying the negative 1 to these ones, you would go, okay, 1, negative 1, 1, negative 1, 1, negative 1. So that does not have a limit. It does not exist. So therefore, this diverges by the divergence test. All right, example 3. Does my series n equals 1 to infinity, negative 1 to the n power, square root of n over 2n plus 3, do we converge or do we diverge? There's my b sub n. Let's go ahead and take its limit. Well, let's see. I have an n on the top and on the bottom. This is technically going to infinity over infinity. So we could do L'Hopital's rule if you want to change it to x's, or, as we did before, you can divide by the n to the highest power, which is n to the first. So if I divide n into every term, this is n to the 1/2 over n to the first. This is getting bigger faster, so this is approaching 0. This is going to approach 2. This is going to approach 0. So 0 over 2 is 0. We made condition 1 true. Now we have to do b sub n plus 1. Is that going to be less than or equal to b sub n? So this means that they're going to be decreasing. Well, working with square roots is always a little bit more difficult to work with because it's hard to be able to combine terms and get a comparison with an inequality symbol. So here you might want to consider changing it into a function and then taking its derivative, and we'll do the first derivative test to see if it's decreasing. So by the quotient rule, this is my derivative. So if you recall, you take the 2x plus 3, put that in the bottom first, square it. Starts off with 2x plus 3 times the derivative of the top function minus the square root of x times the derivative of the bottom function. And when it's all simplified, you get this expression, that function right there. So if we can show that this is going to be less than 0, then we know it's decreasing. So really 3 minus 2x, if you notice, here's the only thing that's negative. Since my x's are starting out at 1 and going to infinity, my whole denominator will be positive. I need to be less than 0, so I need to focus on the top. So 3 minus 2x is less than 0. Add over the 2x. 3 is less than 2x. Divide over the 2. So 3/2 is less than x, or x is greater than 3/2. So here, b sub n is decreasing for n is greater than or equal to 2. Now again, I understand we're starting at 1 and 3/2 is bigger than 1. But again, this is going back to that theorem we had discussed. If we were to take off one term, it still converges and still diverges whether or not that one term is there or not. So again, we're thinking, let's just take off the first term, and it's decreasing for everything. So we consider both to be true, and therefore the original series, it's going to converge by the alternating series test. Example 4. Does my series, n equals 1 to infinity, of negative 3 to the n power over n converge or diverge? So here, we have to factor out the negative 1 off of here. So that's going to be now negative 1 to the n power times 3 to the n over n. So this is my b sub n. So sometimes we have to break out the negative. So there's b sub n, 3 to the n over n. We're going to take its limit. Again, you have both n's top and bottom, so I'm going to consider this with x's, so I can use L'Hopital's rule to take the limit. So taking the derivative of the top, taking the derivative of the bottom. Bottom's easy, that's 1. The derivative of any exponential is itself 3 to the x times the natural log of the base we're working with. Well, wait a minute, time out. This is going to constantly get bigger and bigger and bigger. That's going to infinity. That's not equal to 0. No reason to do step 2. And since my limit does not equal 0, that's your divergence test. So this series will diverge. Again, I'm getting bigger and bigger and bigger. If I just multiply by negatives, I'm going to get a big positive, a really small negative, a big positive. It's just going to bounce back and forth. There is no limit to it. Example 5. Wait, I'm looking at my series here. Where's my negative 1 to a power? Oh, wait a minute. It's hiding here. It's hiding. It's right here. Let's look at cosine of n pi. When n is 1, 1 times pi, that's like 180 degrees. That's on the far left side of the unit circle. Your x-coordinate's negative 1. When n is 2, back over to 0 degrees or 0 radians, that's when my x-coordinate is 1. And I multiply by another pi, add another pi to it, or 3 pi puts me back over to 180 degrees, or pi. And this thing's just going to bounce back and forth, and that's my alternating sign. So I'm going to rewrite this as -1 to the nth power, because I want a negative right away, times n over 2 to the n power. So this is my b sub n over 2 to the n. Let's go take its limit. And again, because you have n's both top and bottom, we're going to change them to x's, and so we can do the L'Hopital's rule. So the derivative of x is 1. The derivative of 2 to the x is 2 to the x times the natural log of 2. Oh, we got a little vice versa going here. Now the bottom's getting bigger and bigger while the top stays 1. This is approaching 0. So now step 1's good. All right, now we got to show that n plus 1 over 2 to the n plus 1 is less than or equal to n over 2 to the n. Now here, again, you could use the first derivative test because we got some exponential functions mixed in with a polynomial function. However, I'm going to be sneaky here. See, the bottom is 2 to the n plus 1. If I were to take this fraction here and multiply 2, top and bottom, 2 to the n times 2 to the first, add the exponents, you get 2 to the n plus 1 power over on the right side. Okay, so now they have the same denominators. So now n plus 1 is less than or equal to 2n. All right, well, okay, subtract over n from left to right. 2n minus n is going to give me 1 is less than or equal to n, or n is greater than or equal to 1, then it is now decreasing for all my n. So both statements are true. So therefore my original series converges by the alternating series test. Example 6. Again, another alternating series, n squared over n cubed plus 4. Remove the negative. Here's my b sub n. We're going to take its limit. And of course, again, you could use the horizontal asymptote rule of rational functions. On your leading terms, if the top power is smaller than the bottom power, then your horizontal asymptote is y equals 0. So as we go out to infinity, you're approaching 0. That's my limit. That's done. Number 2. Now we got to show that, oh, brother, I'm not even going to think about it. N plus 1 squared over n plus 1 cubed plus 4. I have no desire to FOIL this all out, and set it less than or equal to that same fraction. Forget it. I'm converting it to a function, and we're going to do the derivative test. So we'll find the derivative by the quotient rule. So x cubed plus 4 squared. Bottom function starts us off. Take the derivative of the top as 2x minus top function x squared times the derivative of the bottom function, which is going to be just 3x squared. All right, going to distribute and combine like terms, so we're going to get 2x to the 4th plus 8x minus 3x to the 4th. Wait a minute, these two are going to be able to combine together. So that gives me 8x minus x to the 4th, which I can factor out an x if I want, which in this case would be good because, again, we want to show that this derivative is less than 0. So you're looking for, where is my minus sign? What's going to give me negative values? If x is 1 to infinity, these are going to be all positive values. This is going to be a positive value. This is the only factor that can possibly give me a negative. So we're going to set 8 minus x cubed less than 0. We're going to add over the x cubed. Take the cube root of both sides, so 2 is less than x, or x is greater than 2. So again, yeah, it happened here again. We're starting at 1, but we're going to be decreasing once your n's get past 2. So here, technically, we want to take off the first 2 terms, and then everything after that is decreasing. So then technically, again, if you remove the first 2 terms and it's going to converge or diverge, it will still do the same thing if you put the first 2 terms back on. excuse me. So both 1 and 2 are true. So my alternating series is going to converge by the alternating series test. So next, what we're going to look at is an alternating series estimation theorem. It's basically the alternating series test. If you look at everything, hey, my rules are the same. We're just adding on this next statement. Okay? So what this is saying is that the size of the error is smaller than b sub n plus 1, which is the absolute value of the first neglected term. So here's what we're saying. This r sub n is really what they call the remainder. I'm not a fan of that vocabulary because it's really the difference. Remainder, you always think of, hey, I did a division problem. But it's the difference between the infinite sum s minus the partial sum s sub n, wherever we're at. That absolute value has to be less than or equal to the b sub n plus 1, which would be the next term in the sequence that you would add on to s sub n. So, for example, I'm going back and forth, back and forth, back and forth. So let's say we're going to the fifth. N is 5. Okay, so b1 plus minus b2 plus b3 minus b4 plus b5 puts me at s sub 5, which is right here. Now, here's my infinite sum right there. So if I subtract these two, whether I get a positive or negative, I take its absolute value. That distance has to be smaller than the next term that I would add or subtract as an absolute value. Remember, we're taking off the negative because we want the b sub n terms to all be positive. So that distance from s sub 5 to s sub 6, which is your b sub 6 value, that distance is bigger than the distance that you would subtract the infinite sum minus the partial sum s sub 5. So this is, like I said, sum of my series is s minus the partial sum. This is the absolute value of the first neglected term. This is the term that we're not going to add on to the s sub 5. That would be the sixth term. So what we can do is we can come up with a really good approximation of the infinite sum, the s, if you will. All right, so here's what we're going to do. We're going to take this error and we're going to manipulate it. We're going to say, you know what? We need to get rid of these absolute value bars. I'm going to build a compound inequality. So therefore, if I get rid of the absolute value bars, then I'm going to have negative b sub n plus 1 to the very far left. So this difference has to be somewhere between these two values right here. Okay, so for simplicity's sake, all right, here this distance is 1, this distance is 2. Whether my b sub 6 is a negative 2 or a positive 2, my 1 has to be somewhere between negative 2 and a positive 2. It is. It's in between there. Now, I said we wanted to make a good approximation for infinite sum based off of s sub n. Okay, well, on this compound inequality, add s sub n to the left side, the right side, and the inside. So if you add that to all three parts, this cancels. Now I get s sub n minus b sub n plus 1 less than or equal to the infinite sum less than or equal to s sub n plus b sub n plus 1. This will give me a really good approximation for where my infinite sum is going to be. So let's look at an example. Example 7. How many terms of the series do we need to add in order to find the sum with the given accuracy that my error is within 4 decimal places, 0.0001. Okay, so taking my series, getting rid of the negative 1 to the n, this is my b sub n right here. Start listing the terms. All right, when n is equal to 1, b1 will be 1 over 1 times 5 to the first. That's 1 over 5, or the decimal 0.2. We got to convert these to decimals because we're looking for which b term gives me a value smaller than this. So we're going to go to n equals 2. So b sub 2 is going to be 1 over 2 times 5 squared. Okay, that's 1 over 50. That's 0.02. Not yet. Go to b sub 3. 1 over 3 times 5 to the third. That's 125 times 3. That's, what, 720, 775. Just punch in the calculator. 0.0026. Not small enough. B to the fourth. 1 over 4 times 5 to the fourth. Punch that in the calculator. 0.0004. Ooh, we're getting close. I got to go to b to the fifth. Finally, here's b to the fifth. 0.00040 zeros and a 6-4. This is smaller than my error. So, based off of that compound inequality we had, my error, r to the fourth, that difference that absolute value has to be less than b to the fifth, has to be smaller than this value. So we need 4 terms. That b sub 5, that's going to be my first neglected term. So in other words, what they're saying is if we add these all together, you get a value. But as soon as you start adding these numbers onto it, okay, with 4 decimal places there, and I want to be accurate to 4 decimals, and I've got 4 zeros, I'm not going to be making very many changes after I add any of these other terms on, because they're all going to be zeros here. So we're going to find s sub 4, the fourth partial sum. That was negative 1/5 plus. And now remember, we got to look at this as a sum, so we got to put our negatives back on. So when n is 1, we're going to have a negative 1/5. When n is 2, that's a positive 1, 1 plus 1 over 50, minus 1 over 375, plus 1 over 2,500. Let the calculator crunch that all together. There's my fraction, or I wrote it as a decimal. It's a repeating decimal, so I put bar over all the 6s. I don't like to round. I'll leave it as a repeater. All right, so that's s sub 4. And I have b sub 5. So I'm going to go to my compound inequality to make my estimation now. So s sub n, check that, which is going to be a 4. S sub 4 minus b sub 4 plus 1, that's my first neglected term, less than or equal to my infinite sum s, less than or equal to s to sub 4, plus b to the fifth, again, first neglected term. So let's put in all the values. There's my s sub 4. There's the b sub 5. We can crunch these numbers here, both left and right. And I'm going to subtract this on the left. That gives me negative 0.1823306. Went out several decimal places because we're only going to go out to 4 decimal places. So I really wanted to expand this out to show you the accuracy of this. Negative my s sub 4, here, that sum, plus that b sub 5 gives me this decimal. Now remember, we want to be accurate within 4 decimal places. So we got 4 decimal places. 1, 2, 3, 4. This 3 is not going to make that 3 move. Boom. 1, 2, 3, 4. 0 is not going to do anything with that 2. Boom. We're off by 0.0001. That was my error. My infinite sum is somewhere between these two numbers. We're talking out to the tenths, hundreds, thousands. We're out to the 10,000th value. We're only off by 1/10,000th. So I got a pretty good idea that's what my sum is going to be, right in between those two numbers. Now, it's important to understand that this rule that the error is using s sub n to approximate s is smaller than the first neglected term in general is valid for only alternating series. It does not apply to any other series because technically you have to prove that it's a converging alternating series test first before we can show that it is going to be able to come up with some kind of estimated sum. All right? And that wraps up 9.5.